Hey there. Welcome again to another Toolbox Tech Talk. Yeah, well, today's a bit special. Normally I've got my doppelganger here, Guru Glenn, and anyway, I sort of just snuck into his studio and had a bit of a play around and thought we'd just do a Q&A without him because, he gets a bit boring. I think he's probably just sorting through his Tiddlywink collection and his stamps and then just putting them in chronological order or something like that. Really boring stuff. So I'm here with you today, just a general Q&A session. So let's just pull down the tunes. First up, just a shout out to everyone in New South Wales. We here in Melbourne know how you feel. In fact, I think Victoria had something like 192 days of lockdown. It was tough, but you kind of get into the swing of things and it's really tough if you're a small business. So yeah, we feel for you and let's hope things work out faster than they did for Melbourne. Also, I've got a couple of recommendations here. So, something weird happened today. I got blocked from streaming to Facebook. I've never had this happen. Well, I've never been blocked for anything. So I don't know why, but you go to find out and it just says challenge the blocking. It doesn't give you a reason or anything. So anyway, here we are. I'm streaming to my favorite platforms, YouTube, Twitter, and LinkedIn. So you can keep on watching me on these channels while I sort out what's going on with YouTube land, with Facebook land. But I'd also like just to point you through to a couple of other fellow YouTubers in the industry who I think do an excellent job. First up is Finn Peacock. Now, Finn Peacock from SolarQuotes.com.au, he's been making content for a long time on YouTube, very much aimed at the consumer. So, giving advice to the consumer about solar. And he's recently released on his YouTube channel, SolarQuotes.com.au, an installation video in South Australia. And look, the team who did the install did a wonderful job at explaining it at a consumer level, the things you need to know. So probably post this going live, I'll go and put a link up here to it so you can click and go to it. But otherwise, you can search for it, SolarQuotes.com.au. So well done, Finn. You're really adding value to the industry by providing good information for the consumer. The other is a bit more orientated towards the installers out there. That's Mark Kavanagh from MC Electrical. Mark, he's done recently a video comparing microinverters and string inverters using half-cut cell panels and looking at the impact of partial shading. And it's very empirical. Good on you, Mark. I mean, rather than just saying, oh, you should use these, you should use these, he goes, oh, let's have a look at the impact of partial shading and, does a whole bunch of scenarios. So also, I'll put a link to Mark's channel up here, his video, and so good one. Well done, Mark. So today actually is all about you guys and answering questions about solar and batteries and safety standards. But I do have some prepared content, and I also have some questions that have come in over time. So I might roll through some of those, but just, feel free to click the like button, give me a little heart there if you're having a good time, but better still, ask some questions in the chat or comments. So you just go down there and I can reply to them. In fact, I can bring them on screen. So if you're really kind of keen, I can actually bring you in as a video guest to ask you questions. So I'm going to put a link in here. So join live I'm typing this here live, to ask a question. And that means you'll need to have a camera and a microphone on your device. And if you click on that link, it'll pop up in a browser and bring you into what's called the green room here in this live stream. So that means you don't go live straight away. I can see you sitting in the green room, and I can even chat to you via a private chat message, but it's a great way if you want to interact and ask a question and be on screen at the same time. You're welcome to do that. So just check that out in the comments below. You'll see that link to studio.restream.io. For those who are just curious how all this works, there's a service called Restream, and basically, I just stream from my computer here at the Smart Energy Lab out to a service, and then Restream as its name would imply, streams it back out to as many endpoints as I can choose. So, normally that's just the big four for me: Facebook groups and pages, Smart Energy Lab, YouTube channel, Twitter. I've got a Twitter handle there, Glenmo, and also LinkedIn, so my LinkedIn personal page. But that's kind of a bit about the tech of what we do here at the lab. I also can be a bit more interactive rather than just a talking head. And I have some prepared material which I might bring up on screen, which is just some drawings and notes I've made on paper, basically, very analog. And I can use those to answer questions and also interact with the audience. So first up, look, I've had a question actually just about a matter of minutes ago from someone on one of my Facebook groups about last week's Toolbox Tech Talk. I talked about ERAC having made or published a guidance document on the new battery standard, because the new battery standard AS/NZS 5139 did have some ambiguity in it, and particularly around things like that exclusion zone for appliances not associated with a BESS. And the question from Louis was is a switchboard associated equipment? Now, the wording in the ERAC document, and I'm going to just have to bring that up so I remember it, is, hang on a second here, is that you cannot install, and it lists a bunch of equipment, and it says that's considered an appliance, and an appliance as defined in the wiring rules, AS/NZS 3000. So if you go over to AS/NZS 3000, the definition of appliance is a consuming device other than a lamp, in which electricity is converted into heat, motion, or any other form of energy, or is not substantially changed in its electrical character. Now, I can't see a switchboard being defined as an appliance then. So I think it's safe to have a switchboard within that exclusion zone around a BESS. Now, just to kind of make that a bit clearer what we're talking about here, I've got some drawings. Now, this is a little bit of a rehash of something I've done before explaining the battery standards, but not everyone's seen it, so I'm just going to cut to that. So let me just bring the drawing pad up. Okay, here we go. Whoops, got my mic in the way. So what you're looking at here is a little hand-drawn house and showing a battery system here. There's my battery system, and the battery system has this exclusion zone around it. It's also the same dimensions as defined for a fire barrier. So if you have a habitable room, now that's very important, a habitable room behind a battery system in a domestic installation, then you do need a fire barrier that extends those dimensions all the way around. Those are the same dimensions that's known as the exclusion zone for appliances not associated with the BESS. So there you go. That's that one there. Incidentally, that dimension can be deemed to be wrapped around the corner of a building. So it does say 600 mils from either side of the battery system. Now, I should point out this fire barrier is not intended to be fireproof, like the battery can burn for hours on end and the house won't be hurt. It's just to delay any ingress of fire into the dwelling. So if you've got a building, this one's made out of weatherboards, and there is a habitable room behind, in this case it's a lounge, you want to be able to delay any fire being transmitted through into habitable rooms. And so that's what this barrier is all about. And lastly, I've got a little diagram here. This one is showing a house that is made of brick. Now, brick being a material that is deemed to be one of the suitable materials that can be seen as a fire barrier. So brick, concrete block, cement block, terracotta or clay tiles, or a material tested to, and really it's the composite material, tested to a standard known as AS/NZS, hang on, got to write this down here, 5150.1. So that's actually a non-combustibility test for a composite material. So, if you've got a wall made up of different components, it could be tested to this, but that's very unlikely to be done on a domestic installation, because no one's going to go and get their home wall tested. So really, most people would either have a fire barrier of a material like cement sheeting, because that's one of the approved materials, or they would, if it's brick, then they don't have to have it. So there you go. Now I've got my first question come in, so I'm just going to cut back to that. So I'm going to bring these questions up on screen. Here we go, so you can see them. So thanks, Nick. Nick in WA, I hope. And just about no one leaves WA anymore. The world's really getting to be a smaller place, isn't it? We're all just staying at home. So get used to it, New South Wales. How does 5139 apply to non-residential buildings like sheds and standalone cabinets clearly separate from the dwelling? Now, the standard defines a domestic installation, and the domestic installation is defined in various standards based on the building code. So a building which has type 1, type 2, or type 10 is domestic. So it's a freestanding home, a shed, and a multiple occupancy home. They're all kind of domestic dwellings. And it doesn't mean that the shed or something away from the main home is no longer domestic. It's still considered domestic, but you're outside of the habitable room zone. So that's a big plus. Now, once you in a domestic installation install the batteries more than 300 mils away from the surface of a wall that has a habitable room behind, then you're exempted from that fire barrier requirement. So basically a shed or a standalone cabinet definitely would release you from the requirements to have that fire barrier. So I hope that answers your question there. Thanks, Nick. That's great. And keep those questions flowing in, because today really is all about you guys answering your questions. So feel free to throw them at me. And if you're feeling brave, you want to come on live, there's the link in the chat. So to restream.io, you just click on that link and it will bring you up in the green room, and I can bring you on screen with a bit of an intro. So going back to my explainers, another question that came up. Now, this one is also a bit of a repeat from a previous video, but it's a bit more complicated one. I'm sort of diving a bit deep here, and it's about the voltage rating of DC isolators. Now, what happened is that we had an amendment 1 and 2 to AS NZS 5033, which is the PV array standard. And that amendment basically made it easier to make a safer installation by installing the inverter with a built-in DC isolator. So that's a big plus. But we still, under the current 5033, don't get too excited that we've got a new one in the offing. It hasn't been published yet. It's gone through public comment draft phase, but it hasn't been published, so you can't use any of the clauses you might have read about in that public comment draft. But so under the current rules, we are required to have an isolator adjacent to the array. So you still will be selecting a DC isolator and therefore have to consider its voltage and current ratings. Now, the amendments 1 and 2 to 5033 actually introduced some new terms and understanding what the rating of a DC isolator is. Previously we just had two things we looked at. There was a maximum voltage and a maximum current. But actually now that we've got what we call the thermal current, and then we've also got the I make and I break current. Now, those I make and I break are generally significantly higher, 4 to more times higher than the operating current capabilities of the DC switch. So introducing those as part of the consideration comes from an IEC standard, IEC 60947.3, 2018. Now, that standard defines how you calculate I make, I break, I thermal, etc. And we also introduced a couple of temperature zones where you may have a DC isolator installed, like not in direct sunlight, but in an environment where it's exposed to a high temperature, such as on a roof underneath appropriate shield, would be a 60-degree rating for all of the currents. And in a shaded location, like on a veranda or a carport, it would be the 40-degree rating. So we've got two different I thermals that we can consider as part of that assessment. So let me just bring over that slide. Here we go. Gotta get my mic out of the way. Right, so just bring that down a little bit. There we go. So determining isolator voltage ratings. These are the key things that you need to consider. The type of inverter, is it separated or non-separated? Now, what we mean there is, does it have a transformer or no transformer? And we're using the word PCE, power conditioning equipment, which would include things like maximum power point trackers, charge controllers. So they're PCE. Basically, since probably the last couple of years, there hasn't been any non-separated inverters on the Australian market. I think Fronius with their Galvo was the last one. So they're all non-separated. And when they're non-separated, that basically means that you can have a fault to earth through the inverter, through the MEN, back through the transformer to earth. And therefore, on the DC side, only one pole or one switch leg, more correctly, of the DC isolator may be interrupting a fault current. So it sort of more or less doubles the rating. So you need to know what the topology is of the inverter or PCE. You need to know what the open circuit voltage of the PV array is for the lowest expected temperature. That's not just, I think it gets cold around here. Just check on the BOM what the lowest temperature is, maybe add a few more degrees, and that's what you're going to be using to calculate your VOC max. The PV array short circuit current is from the data sheet for the panels, and then times 1.25. So that's the 25% overload rating is a conditional. And then we've got whether it's the location of the isolator. Is it indoors, outdoors, or is it outdoors and shielded? And that then brings us, moving this up a little bit so you can see better, to the definitions from 60947.3. So there's rated operating voltage, which is referred to as UE, U being kind of European for voltage, IE for rated operating currents, I thermal for conventional free air, and ITHE for conventional and closed thermal current, i.e. in an enclosure. And then we've got our I make and I break. Now, all of those sometimes are really quite hard to find. I went and looked up a brand that I hadn't heard of before just the other day, and I couldn't find the I make and I break. I could find everything else. And it had been tested to IEC 60947. So I guess part of the problem here is, and I was going to cut back to me for a sec, the problem here is that Australia and New Zealand, with our kind of really hardcore standards, are a small market for the world, and manufacturers don't always consider all the intricacies of our standards, but some of the good guys do. So, you'll find some isolator manufacturers provide you with exactly the requirements that Amendments 1 and 2 of 5033 incorporate. So the other thing that you need to consider, we've got some questions coming in here. I'll come to those, Trevor. Nice to see you, Trevor. And Jennifer. Yay, shout out to Jennifer. You've been on my channel a bit lately. Great. So just cutting over to the next step in utilization categories from 60947. And apologies if this is sounding awfully geeky. I've got some lighter stuff coming up, but I try to attend to a wider audience. So a bit of it's a bit for the installer industry, and it's a bit for the consumer industry. Stuff falling over here. So I've got everything's held together with chewing gum and tape, just to kind of keep it all nice and tidy here. I had to counterweight my microphone. It's kind of floating up in the air. There we go. And if you're kind of wondering how all this looks at my end, I think I've got a camera on it. Where we go? There we go. That's the setup. I've got a lot of screens to look at while I'm trying to manage all the tech and keep the stream running. So cut back to, where are we? Back to this, and take me out of the key. There we go. So that's the utilization categories that we need to consider. So what are they all about? Effectively, when you interrupt a DC current, it releases a lot of energy, and that's the kind of the problem with DC, is that it likes to continue an arc. So it will sustain an arc for a long time. And when I say long, milliseconds after a gap has been formed. And that's often enough to melt contacts and create a hazardous condition within the switchgear, and often enough heat to melt stuff. So that utilization category is defined here. And DC-PV2, which is replacing the old DC-21B. 21B used to be being able to operate once every 30 seconds. So that was a pretty long cooldown time, 30 seconds of cooldown. But DC-PV2 has a requirement for significant overcurrents in both directions. So it's a much tougher rating than the old 21B. We also require ingress protection, IP56 no water, NW for no water, and that's for outdoor enclosures that are tested to IPX6 and must have no water ingress. So yeah, basically, if you're putting an isolator out in the weather, you don't want any moisture falling inside it. The thermal effects that we consider are based on location. So if it's installed indoors or outdoors in full shade, we rate the current settings at 40 degrees Celsius. But if it's outdoors, where at a 6-degree ambient, where enclosure or shrouded will receive direct sunlight. So the air isn't 60 degrees, but you're getting up to 60 degrees underneath that shroud. So I might just pause for a second because we've got a couple of questions coming in, and I just want to keep this stream running with the questions. So that's great. Now I'll just cut over here. All right. Trevor asks, any regulation for sealing material above the BESS? Well, actually, it's exactly the same. So the requirements is that the requirements are that if the top of the BESS, and that actually is not just the battery system, but if it's an all-in-one, it would include the ancillary equipment as part of the all-in-one. So particularly tall BESSes like your Alpha ESS, your Redbacks, a Sonnen with its full cabinet, there will be, typically 1.8 to 2 meters high altogether. And that means that you're going to have to have 900 mils above the BESS with a fire barrier if there is a habitable room behind, Trevor. So if you've got an eave, that means that you can't get 900 mils above. You have to line the ceiling and or eave with the same sort of material that you'd line the wall. Typically, cement sheeting is the preferred option. So hope that clears that up there. Thanks, Trevor. And I got one from Jennifer. Hi, Jennifer. And she says, hi, Sybil. I don't know how I got to be called Sybil, but anyway, you're probably thinking of that other dude. What were the brand of the corrugated roof mounts you did a box opening on a while back? Were they S5? Yes, they were indeed, actually. And by the way, I just happen to have one here right next to me. So that's kind of timely. Sybil, I've been installing a system on a roof profile here in Australia known as the Clip-Lock 700. So it's basically a more often in a commercial environment, you'll find this type of roof profile. It's ColorBond branded in Australia and New Zealand. It's a high tension steel roof with large flat pans with little ridges every 200 or 300 mils. And those ridges need to be clamped to. And so what we got here, see if I can get it in the camera quite well. What we've got here is the S5 system. Now, this is really a departure from what I'm used to. Normally, I'm used to putting what they call L feet or some other base, and then put rails on top of those. And the rails span the whole width of the array, and then the panels sit onto the rails, and therefore there's clamping onto those rails. But S5, for those in the US are probably quite familiar with S5, they've been around for a long time. They've entered the Australian market with their products, and I'm doing some testing here and some training content for them at the Smart Energy Lab. So this system here has a little, if I put it around the right way, a little lug that goes in here like this, and you tighten up the bolt, and it squeezes onto the ridge of the, I'm too close to the camera. It squeezes onto the ridge of your roofing material. So, and then this is the clamp that clamps the panel, and this disc here is actually It's got very sharp points all the way around. It's your earth bond. So it bonds the panel directly onto this standoff. But because of our regulations in Australia and New Zealand for continuous, not daisy-chained earthing, we have to additionally run a trailing earth basically all the way around the array. It's not a big deal. We just use earth clips onto each panel, and we have a separate earth cable that runs around the perimeter of the array, so that all the panels are connected all the time to massive earth. And if you take any one panel away, you don't compromise the earthing of the whole system. So that's the S5 system. They also do make ones for corrugated. They're called the CorruBracket. That was exactly what your question was, Jennifer. The CorruBracket's designed for corrugated iron, and it screws on rather than clamps on using their custom screws. I haven't got any in arm's reach, so I can't actually show them, but yeah, I did do. I might even be able to link to it up here if I remember, so you can watch it after the event. So thanks a lot, Jennifer. Might change my name to Sybil now. And all right, there's a follow-up question from Jennifer. And anyway, to get some serious tilt on those for bifacials with tilt rather than laying flat on the roof, yeah, look, I haven't actually seen what the tilt solutions are from S5, so that's something to look at. And you do mention bifacials, and you mentioned tilt. That's a really important note. So Jennifer's across this issue. When I first came across bifacial panels, I got super excited. I thought, that's great. They're always going to be better. So why don't we just always use bifacial panels? Because, at least the back's going to pick up something. But actually, I was told by PV engineers that that's not quite true. A normal module with a backsheet has internal reflection. And so you're getting some bounce back within the cell, within the glass, basically, to the back or the rear of the cells because of that light-colored, typically white backsheet. Now, if you take that back sheet off in the case of a bifacial module, and you've now got a dark roof underneath it because you haven't inclined the panels away from the roof, they're parallel to the roof, you're actually losing some of the potential. So I guess the take-home message is bifacials, to get best performance, do need rear irradiance. I mean, if you're on a flat roof and you tilt the panels and you paint the roof white, that would be great. That will definitely give you the best bounce for your buck. If you're doing a ground mount system, the albedo of the earth is excellent. We've got a 70 kilowatt tracking array here, half bifacial, half mono perk, identical panels, and I do notice under certain conditions the bifacials outperform the perks considerably, particularly fog. When we get bright fog, which isn't really something you want to look forward to, the light's coming from all directions. But also on a hot sunny day, when you've got the panels inclined at some angle, you're getting a lot of rear bounce off the grass. So dry grass reflects quite a bit. And we're actually planning on putting down white pebbles as a permanent reflector too, just to get even more bounce. So let me know how you go, Jennifer, with the tilt solution. I'll be very keen to see what you come up with. Anyway, thanks for those questions. Keep them rolling in. And I did say I'd finish off with my little example of a DC isolator. So I'll just cut over to that. Make sure I've got the right one. There we go. Yeah, so this is a worked example using LG Neon's panels, their 365 watt module, and there's the data sheet information that you need to get. So I better pull this down a little bit so you can see it. There we go. There's the data sheet information, what the VOC at standard test conditions are, but we need to know what the maximum voltage at temperature compensated. So we look it up from the table in 5033, and we find out that at -5, which is pretty cold, those 13 of those modules will go up to 597 volts. So that becomes our voltage rating that the isolator needs. We know what the ISC of a module is, and if it's a series string of 13 panels, it's still 10.8 amps. In a series string, you don't increase the current, just the voltage. So therefore, we need that safety margin for overload of 1.25. You might wonder why. It's because panels are tested at 1,000 watts per square meter of irradiance, but that's not absolute. And so you can get conditions where you get higher than 1,000 watts of irradiance, and that will actually correlate directly to more current. So current is more or less directly proportional to irradiance. The DC isolator is being installed outside in direct sunlight, but with a cover just to protect it. And therefore, we look at the thermal rating for 60 degrees, because ITHE is for 60 degrees rating. And from the data sheet, I used the ZJ Benny. I looked it up and they said 29 amps. So for the particular product I was looking at, 29 amps is what the thermal rating is, and we only need 13.5, so we're good there. The number of poles switched under normal operation is 4 poles. So that means that there'll be a rating for the voltage rating of the product with all 4 poles switched. But because we know that we, in this case, connecting it to a transformerless inverter, under fault conditions, you'll get a fault path that'll only go through one switched leg of the DC isolator, because it's got a path to earth through the equipment and doesn't have to return through the other leg. And therefore, it's only 2 poles that it's operating at. So we need to know what the voltage rating is for 2 poles in series. So there you go. That's the level of detail that you require to meet 5033 Amendments 1 and 2. All right, I'll better take Jennifer's question off the screen. Sorry, I still got it there. There we go. All right, how are we doing? Everyone's quiet. No one wants to come on live. I would have loved to have a few audience members join me on screen. Even if you're on, just on your mobile phone, it still works. You can just kind of click on that link. And in case you didn't see that link, it's in the chat. I might just copy it again, throw it in there for you. There we go. That's the link. So yeah, if you click on that, you can come to the green room and get your camera and audio turned on, and I can bring you on for a chat. You don't even have to ask me a question. You just might want to say hi. I'm trying to make this as interactive as possible rather than just being, me talking to a camera. All right. So Nick, let's have a look at this one. Bring Nick's question up. Thank you, Nick. And it's a Nick Graham, so it's a different Nick. Cable entry into DC isolators. Do they need to enter the bottom of the DC isolator in indoor locations, or is this only for outdoor locations? Thanks. Well, actually, I guess, Nick, this question comes down to what jurisdiction are you installing under. For those who are not familiar with Australia and New Zealand, we follow a standard called ASNZS 5033 for PV arrays, and so that's what Nick will be referring to. But additionally to that, we've got incentive programs, financial incentive programs, such as a small-scale renewable energy scheme and also state-based incentive schemes for solar. And both of those have additional rules that come into play, and most notably compliance with the Clean Energy Council's design guidelines. And so you'll find that there'll be information that's provided as guidance, but actually is mandatory under those economic programs. You'll also get a variation of interpretation on this as well by inspectors, or whether that's your energy safety regulator, whether it's the federal regulator, Clean Energy Regulator inspectors, or whether it's actually a state-based audit program. So here in Victoria, we've got Solar Victoria have their own audit program. So you get audited quite a lot here in Victoria, and therefore I would suggest that you try and avoid being picked up for absolutely anything, because they're bound to find it eventually. Now, the question here is, do they need to enter from the bottom of the isolator? Now, this came about because the CEC guidelines quite some time ago showed bottom entry, and then that got adopted into examples in 5033 in amendments, I can't remember, it's 1 or 2, and that's really about water ingress. If you've got a top entry, even if you think you've sealed it, you've got a plain screw adapter and you've glued the corrugated or rigid conduit into it, and you think, I've done a good job, you still get water puddling around that connection point with the isolator. And there's a very good chance that with disturbance and over time, shrinkage, thermal expansion, contraction, some water may puddle and then get in. So bottom entry is just a safer way of ensuring that there's no ingress of water into a DC isolator. But in an indoor location, really it's more likely that the conduit itself will be the plumbing system that brings water into it. And that means if you've got open-ended conduits on the roof, which you are supposed to seal with the multi-hole gland, by the way. But if you haven't, you will get atmospheric moisture, drips, or even direct water ingress straight into that conduit, which becomes part of the plumbing system to take water down to the DC isolator adjacent to the inverter, if there is one, and fill it up. Doesn't matter if you're top entry or bottom entry, it'll eventually fill it up. So, yeah, water is your enemy. By the way, standards are really trying hard, and certainly some of the safety regulators too, to get rid of this problem, particularly at the inverter, by using integrated DC isolators. Now, this actually relates to another question. Nick, I'm just going to take your question off the screen for a second. I had a question come in about, can you use the integrated DC isolator built into most inverters these days, most grid tie inverters, as the DC isolator adjacent to the inverter? Well, the answer is yes and no. The answer is yes if it complies with Amendments 1 and 2 of 5033. And there's some very specific requirements in there, but most notably that the switchgear is tested to IEC 60947.3. The manufacturer has a declaration for that. It's also, there are no accessible live DC parts. So that's generally not an issue if there's no serviceable part areas within the inverter. So there are many inverters that are fully sealed. There's no serviceable parts inside, and repair is by replacement only. So in that case, the integrated DC isolator is the isolator adjacent to the inverter. I would even go as far as to say that it's being recommended now by, in Victoria, Energy Safe Victoria, in a recent publication, state very clearly, and I'm just reading it off the screen, ESV, that's Energy Safe Victoria, strongly recommends using inverters that contain an integrated DC isolator because of the problem of having external DC isolators and water ingress and all this top entry, bottom entry palaver. So there you go. Oh, a few more questions come in. And I've even got a guest. Hey, Brendan. I'll come to you in a second, Brendan, while you just get yourself sorted there. That's great. My first live guest sitting in the green room. Brendan, just for your comfort, you can't be seen by anyone but me. Yeah, that's why we call it the green room. Now, I think I've answered that one. And here's another one from Jennifer. Thanks, Jennifer. Set up Super Chat so we can shout you a Bundy and Coke. Yeah, I'm not really, I didn't know about this Super Chat thing until recently, so I must try it. Thank you, Jennifer, for alerting me to this one. I think whiskey would be the go for me, but definitely that's a very nice thing to suggest. Thanks, Jennifer. Nick Stone again. Glenn, with darker days typical of this time of year, actually, we've had the most glorious few days here in Victoria. It's been sunny for like 4 days in a row. It's unheard of in the middle of winter anyway, especially with regular fronts coming through. Are there any learnings on battery storage performance relating to days of autonomy? Now, great question, Nick. Days of autonomy. What Nick's referring to there is how many days without renewable energy input is the system designed to run for? And no backup options. So let's say like we had a storm recently in Victoria that caused significant outages around the Dandenong Ranges, and people lost power for up to 3 weeks. They're only just being reconnected, some of them right now. And so you wonder, how many days can I run off the battery storage system? But autonomy is assuming that there is basically a total eclipse for those, number of days, because we're not considering any input at all, even low cloud, low irradiance. So what are the learnings? It really comes down to what your objective is. Do you want a system that's going to give you 1 hour of backup, 1 day of backup, 1 week of backup? And that's when you start to look at capacity of your storage system based on your energy demand. So, yeah, there's good. Now, Brendan, are you nearly ready? I can see you just moving, coming and going a little bit there. Maybe he's adjusting his camera. Looking at someone in the green room. Are you ready? There we go. So thumbs up if you're ready to chat, Brendan. Not sure. I'm not sure if you can hear me, Brendan, but if you're ready to chat, just give me the thumbs up. Yep, I got the thumbs up. Okay, I'll bring you on. Here we go. G'day, Brendan.
Just the chat has covered your entire picture on this phone.
Yeah, it's pretty tough on a phone, but I can see you perfectly, and so can the audience. Go ahead.
Right. Is that working?
It is indeed working. Everyone can see you. We're split screen, so I'm on one side and you're on the other.
I sent you a message which you haven't published, but yet.
Oh yeah, I can see it in the chat. Yep. Do you want to just?
Okay.
Oh, I can bring it on screen.
I'm trying to get my. I'm trying to get my solar put on, but I've had the second phase put on, but it doesn't connect.
Okay, so just for those who are not familiar, AusNet is a network service provider in Victoria, one of the 5.
And I can't contact AusNet. Obviously, they're busy with all of those people that have lost their connections.
It's probably the worst time they've had in decades as a result of the storm, particularly in the Dandenong Ranges. So, yeah, I guess they're a little bit overloaded. But generally, you don't directly contact the distributor. It's normally something that you're
I might have to give this up.
Okay. I think Brenda's having a few technical problems there, but normally you don't directly contact your network service provider unless there is an emergency or a fault. Generally, it's through your electrician. And in the case of Brendan, he's trying to get, from the sound of it, a dual phase connected, so 2-phase system, which here in Australia is sometimes referred to as a SWR, single wire earth return. And he's having problems because the approval process, which is an online tool from AusNet, hasn't been updated. So I'm not familiar with the that particular problem. So sorry, Brendan, I can't really help you with that one. But there you go. Oh my God, someone's just sent me a super chat. Wow, thank you, Jennifer. Amazing. And Frank says, hi. Look, Frank, you win the award. I call you my serial offender because you've done my course so many times. And you've been a wonderful supporter of the Smart Energy Lab, including leaving bottles of wine at my back door. So you are the first kind of super chat that I've ever had. Thanks, Frank. Yeah, we'll pop that out. And thank you, Jennifer. Wow, look at that. Don't know how I collect it, but there we go. I'll find out later. An A for effort from for Brendan, says Jennifer. So yeah, cool. Right, really, this is great. Getting the juices going here. Now I'm going to go back to Techie Land now and talk a little bit about different ways of AC coupling solar and battery systems off grid. Now, the terminology AC coupling gets thrown around like it's a sort of generic solution, but actually there's lots of ways of doing it. And I'm going to limit my choices to off grid here. And you might wonder, well, why would you choose AC coupling as opposed to DC coupling? Because DC coupling actually is the oldest. It's been around for a long time. And it's actually having a bit of a comeback, if you ask me, because of really higher voltage capable charge controllers these days. And also because of the independent way they charge batteries, independent of any AC source. You don't have to worry if the generator's working, the inverter's working, they'll just charge a battery. But that's another day, and that's another story. I'm going to look at generic AC coupling next. So let's just bring that one up. Okay. Get one of my screens on. Okay, there we go. So, yeah, so what you're looking at here is a drawing I made of a AC coupled system. I'll just try and get it nicely centered for you. There we go. And it's off-grid. So we've got a generating set connected to a battery inverter. Now, battery inverters for off-grid often are capable of charging a battery at the same time as supplying the loads, which is an interactive inverter. In fact, there used to be a special thing. Now they're pretty much what you'd expect of any quality off-grid inverter to be able to do. Therefore, you've got two AC ports. We've got AC source, which is the source of charge, and we've got AC load. Well, notionally, it's where it supports a load. But it's possible for this to be bidirectional, this port. Now, look, a warning here, not all inverters that are bidirectional capable. Many so-called hybrid inverters, which are designed for on-grid applications with backup, aren't designed to receive energy on their backup port, but off-grid inverters often are. Then we've got a solar inverter over here. The solar inverter's got a PV array connected to it, and the PV array, being DC, is converted to AC, and that AC feeds the load center first, and then any surplus actually can flow all the way back to the battery inverter. And the battery inverter then, being bidirectional, can charge its battery system. So this is what we call AC coupling, because the way that the DC from the panels gets to the DC in the batteries is through the AC network here. So it's all, the coupling is on an AC network. But we do have a little problem when we're off grid that we have to solve. What happens when this battery system is at a state of charge of 100%? It can't accept any more charge. We can't send, and it's a sunny day, so let's say we've got 10 kilowatts of PV here, and it's pumping. What's going to happen to all that energy? Let's say the loads are drawing 1 kilowatt of load energy, or load power, sorry. It's got 9 kilowatts spare. Where does it go? Well, unfortunately, we can't send it back to the generator and convert it to diesel because they're a one-way device. We can't send it to the battery because it's full. So what we have to do is very quickly curtail or reduce the generation coming out of this solar inverter. Now, there's a couple of ways of doing this. The most popular and common way to do it is what's known as frequency shift power control. Now, what that means is inverters, and in Australia and New Zealand, our grid standard already requires this in all on-grid inverters anyway, is that if the frequency starts to rise above 50.2 hertz, the inverters will start ramping down. They'll reduce their output. And typically, depending, you can adjust these set points, but at 52.5 hertz or thereabouts, they will have reduced their output to 0. So they don't just turn off, they ramp up and down based on frequency. So what changes this frequency? When the generator is running, the generator basically sets the frequency. So it will probably, depending on how stable it is, cause the solar to reduce anyway, because unless you've got a generator that sits very nicely at 50 hertz, it's going to create a slight frequency shift on the grid, on this constructed grid here, and the solar inverter will start to reduce its output power. But when the generator is not running, so we'll take it out of the equation, the battery inverter sets the frequency. And this is where frequency shift power control comes into perfection, is the inverter basically controls the solar inverter by shifting the frequency. So, you know, if I draw a little graph of frequency versus power, so this is 50.2 hertz here, and this is 52.5 hertz. Now, these will be different for those in North America of the 60 hertz grid. And this would be 100% power here. So this is the power rating of the solar inverter, and this is 0% down here. So it basically ramps up and down over that range by changing the frequency that the inverter is setting. So the battery inverter sets the frequency and controls the solar inverter. Now, I'm just checking for any questions that have come in. Okay, none there. All right, next one. Now, you can actually do the same thing with a hybrid inverter. Here, I'm showing an inverter that has its own battery, its own solar, as well as a dedicated battery inverter. Now, this would be a fairly unusual kind of design, but one of the use cases for this would be where you've got an undersized battery bank. Let's say this has a capacity of, let's say, oh, that's a bit big. I'll make it 30 kilowatt hours of storage. So we've got 30 kilowatt hours of storage in our battery bank here, and it's for an off-grid home, and that just turns out to be too small. Now, depending on what these batteries are, if these are old school lead acid, I'm not trying to diss lead acid, it's still got a role to play, but it is 150-year-old technology and it's still going. And it is, by the way, the most recycled product on the planet still by weight. It's not easy to upgrade a lead acid battery system. You really use it and then recycle it. You don't add more cells or parallel strings to it. It just is a bad design idea. But what you can do in this case is add more storage on this side of the equation. So we basically got a hybrid inverter with its own battery system. Now, there's another magic piece of equipment in this arrangement, which is a consumption meter that measures the energy flow at this point here. So we need here a meter. This meter is measuring, are we importing or exporting energy from the battery inverter? And that meter is communicating with the hybrid inverter. Now, this is exactly the arrangement that you would have with an on-grid system, that the hybrid inverter would have a meter at the main switchboard measuring the exchange of energy with the grid. But in this case, we're off-grid. It's measuring the exchange of energy with the existing battery inverter, and therefore it's trying to supplant any use of energy from this battery inverter. It's saying, use me first, use my solar panels first, then use my batteries next to supply the essential circuits. And when it's run out of puff, it's nighttime, so there's no solar, and the attached battery has gone down to its minimum SOC, then this old system takes over. So basically, you're putting out to pasture your old lead acid system. But I should point out this would be a pretty narrow use case, because these days there's a lot more modular batteries being installed. I've here at the Smart Energy Lab have what I call the Tower of Power from Power Plus Energy, and it's got 20 battery modules in it. We could easily add another Tower of Power, hint, hint, next to it and put another 20 in. So you can add them one at a time, and they're all in parallel, and they just increase capacity. So that's a nice thing about modular battery systems. All right. Looking over at the questions again here. I was going to switch back to main camera. All right. Jennifer, you're great. You're asking lots of questions. Thanks, Jennifer, for turning up. Can we also use a dump load so it does not go to waste, like water heating, etc., instead of frequency shift? Absolutely. Curtailing renewable energy generation is the last thing you want to do. You're only doing it because you've got no other choices. And the simplest way, as Jennifer points out, is a switched dump load. So there are many products on the market that can do this, and sometimes the inverter itself, the battery inverter itself, has this functionality. So based on state of charge or voltage or other parameters, it will turn on through a voltage-free contact a load, and therefore turn on a water heating system. But one of the problems with that is if the load is big, there is a chance that it will start to discharge the battery. So to give an example, you've got a 3.6 kilowatt element in your hot water service. Your batteries are full, and there's 1.5 kilowatts of surplus solar coming in. So you turn on your hot water service, or the system does. But what that means is only 1.5 kilowatts of renewable energy is going into that hot water service. The rest is coming out of the battery. It was renewable too, but it means you're starting to discharge your battery. A better solution is one that responds proportionally. Now, there's a few solutions here. There's quite a lot of companies that are selling products into Australia and New Zealand, which are power diverters. Now, they're mostly designed for the on-grid market. There are some that work off-grid as well. And what they do is they have a CT or other means of measuring the amount of surplus energy, and they proportionally send AC power, variable AC power. Now, you might think, well, can you do that? Yes, you can. So you don't actually have to send a full wave shape. Sinusoidal wave can be chopped up into segments and send in a smaller proportion and then to the hot water element. Because a hot water element really doesn't care whether you give it full power or a tiny amount of power. It starts to heat, but its heating rate will vary. There are even, Jennifer, frequency-controlled hot water elements. I've got a few of them here at the Smart Energy Lab. I've got one from an Austrian company called MyPV, and the product's known as the AC Thor. I've got a 3-phase unit that's 9 kilowatts. So it'll divert up to 9 kilowatts into my hot water service, which really cranks along nicely on a sunny day. They have a single-phase one as well. There are other services that use that frequency shift. I'm just trying to think of one off the top of my head, but that's the one I'm most familiar with because I've got it here at the lab. So frequency shift load dumping is really a great way of doing this because it works in inverse to the curtailment of frequency controlled power. Great question, Jennifer. Thank you. looking at Brendan now. Next up, Brendan asks, would the same work with Grid Connect rather than a generator? SWIR lines are limited to 3.5 kilowatt export. So unfortunately, Brendan, once you're connected to the grid, you can't change the frequency. So the only way of changing the frequency is to be disconnected, whether it's temporarily or permanently, from the grid, because the grid is an immutable force in terms of frequency. So no, you can't. I think, Brendan, you've also got this problem of having a 3.5 kilowatt limit per phase on SWIR. SWIR unfortunately is a very limited capacity. It's kind of a bit of a cranky system, but some people have no choices. So living with a SWIR will mean a rather small export limit. But can I encourage you to just ignore export? There's less and less incentives in Australia and New Zealand to export energy. The payback is way less than using it yourself. So trying to find ways to consume solar when the sun is shining, or with the battery to capture it. Those are the best ways of doing it. Using it is the cheapest. Putting sort of scheduling on for appliances so they soak up your solar when the sun's shining is a simple way to do it. Thanks, Brendan. Okay. Yes, Nick. Yeah. And Nick asks about pulse width modulation. So if the question is, what is pulse width modulation? Pulse width modulation is where you are changing the time between on and off. And that's one way of controlling the amount of energy that's being transferred. So, for instance, DC maximum charge point trackers generally use a voltage transformation, but there is a simpler system known as PWM, or pulse width modulation, which basically turns on and off the current going from a solar panel to a battery at a very rapid rate, typically kilohertz rate. And by adjusting what's known as the Mark space ratio, it's an old term from the days of telecommunication, which is where I come from, changing the Mark, the on-off ratio, determines the average amount of current that's flowing. So it's another way of curtailing charge. So PWM. It's also very simple to do. Trevor says, how about heat pump, load dumping, air conditioning, or hot water? Well, anything that requires a startup procedure and a shutdown procedure, like a heat pump, is a bit tricky. You don't really want to just turn it on and off at whim. You need to let it go through its cycles and pressurize and then do its job. So generally, heat pumps and air conditioners need a smart controller, something that will send a signal to it to turn on, and it then controls its on and off independently of the supply. But with hot water, if it's a resistive element, which though it is the least efficient way of heating water, if you've got plenty of surplus energy, it doesn't really matter, and it's super simple to dump energy into a resistive element. So there's a couple of choices. Okay, right. Now go back to my techie thing. Where was I up to? That was AC coupled. And now moving up to something a bit bigger, which is microgrid. Now, microgrid is something where you have more than one battery system and or PV connected across multiple locations. So let me just share that one. So I'll turn off your question there and bring up the other screen. Okay, there we go. So let me explain this microgrid. What happens here is we've got a central grid forming system, and in this case, I'm calling it the microgrid battery inverter system, and it sets the frequency to which everything else synchronizes. But across that AC network, and these may be multiple buildings, for instance, not necessarily all co-located, that you may have solar inverters connected at one point. You might have hybrid inverters, solar and battery, and you might have just battery inverters. They may even have their own DC coupled charging as well. And all of these systems are feeding in, and this is drawn as a three-phase system, but it doesn't have to be three-phase, into a common AC bus. And in this case, we need to control, once again, all of these sources, whether they're charging or discharging from the microgrid. And that's done with frequency once again. Now, this is came as a bit of surprise to me. It's very simple. As long as you comply with some of the manufacturer, or all of the manufacturer's requirements in terms of ratio of the microgrid battery inverter to the ratio of generation systems that are being controlled by frequency. When I say ratio, power ratio, then it just works. 4777 Part 2, which is our grid protection standard in Australia and New Zealand, mandates frequency shift power control as well as voltage and VAR ramping as well. And it just kind of works. So anything compliant with 4777 Part 2, 2015 and beyond automatically has this feature. But there are some limits to how useful this can be, and one is the rate that it can do it at. Frequency shift, the limit is your frequency. So if you're 50 hertz, you've got 20 millisecond cycles, and that's as fast as you can respond. You can't change the frequency quicker than that. But if you want to have really fine-grained control, this is the last slide in the series, is using comms. Now, this is actually the system we have, one of the systems we have here at the lab. This is for 20 kilowatt select sun inverters connected to 70 kilowatts of PV array on a tracking system. And all of these inverters are controlled by this pink dotted line. This pink dotted line is an RS485 comms cable. And the RS485 comms cable goes back to the battery inverter. And the battery inverter basically tells all of the solar inverters exactly how much energy to produce, up to a maximum, I should say. They can't tell them to produce energy in the sun at nighttime, and therefore you get very fast control. It's way faster than frequency shift, and it's a more responsive solution. But it's proprietary. It means that this battery inverter has to be able to talk to these solar inverters. So you're locked into a proprietary solution. There we go. All right. Another question. Let's cut back over. Okay. Scott. Scott asks, does pulse width modulation, not PMW, but PWM, cause electrical noise and radio interference? You bet. It depends on how much dampening there's done. But when you're switching something, you get transients, and transients create broad spectrum interference or emissions, and those emissions can often be picked up, particularly in the the longer wavelengths like AM radio. I remember driving to a customer, well, it was actually an upgrade job here in Melbourne and on the outskirts of Melbourne, and the customer was off grid and wanted an upgrade, or actually they wanted a fix. That's right. They said the system wasn't working. And as I got to his front gate, my AM radio started buzzing. As I drove closer to his house, I couldn't even hear the radio anymore. All I could hear was noise and distortion. And I was going, oh my gosh, his house is like an RF nightmare. And it was just a little charge controller on the wall that was causing all this noise. Now, I won't go into the intricacies of how do you dampen RF interference, but definitely switching is one of those. And it is actually a requirement in Australia to meet ACMA's requirements for not generating RF interference, but it is a self-certification program. So sometimes it's the bad guys get caught out when there's a problem and they have to turn it off. So yeah, PWM, just it is possibly a little noisier, but there are ways of limiting it. Trevor says, I'll pump some water then to a header tank and store my solar energy as potential energy. Trevor, you're a man after my own heart. I often think of water stored at height as a battery, because that's what it is. It's stored energy and you can use it whenever you need it. I love it in off-grid designs because it means you've got resilience. The last thing you want to happen is that your inverter fails, and that means you've got no AC power, which means that your pressure pump doesn't work, which means your taps don't have any water coming out of them, your toilet can't be flushed. Suddenly life gets pretty bad quickly. Even worse, if you're in a bushfire affected area or potentially affected area, the last thing you want to lose is water pressure because of an electrical fault. So having an independent source of pressure, even if it's relatively low, is a nice bit of resilience. And you can store a lot of water very cheaply. Here at our little cluster of houses, we have a 260,000 litre tank, which we pump water using surplus solar energy to, and that's seasonal storage. Effectively, we can store months worth, like about 3 months worth of water in there. So the surplus of energy from summer is being stored as water, and therefore it doesn't take away from our winter energy consumption equation quite so much, because we're using water that's at pressure without having to use electricity. Yep, Trevor, that's a really simple and practical solution. What's this one here, Trevor? This site has declared a bromance-free zone for everyone's safety. Okay. Yep. Back to Jennifer. My experience has been that you get RFI QRN on both PWM and MPPT, but it's easily quenched with about 20 turns through a mix 31 ferrite. Absolutely. So there are lots of ways of designing out RF interference, and there's lots of ways of introducing it as well by not doing the right thing. So, yep, ferrite cores are a common way of reducing this interference exiting the appliance. Thanks, Jennifer. And she also adds 1 ferrite on each leg with a foot of solar charge controller. Doing this 20 turns cut my RFI problem to 0 in my ham shack radio. So ham radio operators really understand this because they're working with little signals that travel halfway around the globe, and they don't want them interfered with. So yeah, you've got to be good at this. Thanks for that one, Jennifer. Oh my gosh, we're nearly out of time. And I think I've probably covered just about all of my material. So well, this has been a really fun Toolbox Tech Talk. I've been doing a few pre-records, people might have noticed. It's because I've got a family and I sometimes have to spend time with them on a Sunday and, other things. So I've been, doing a few pre-records, but actually I love doing these live events and having you, the audience, turn up and ask me questions and even try and pop in live. Thanks, Brendan, for giving it a go. Good on you. But I also welcome questions for my next Toolbox Tech Talk. And so if you want to send them in through comments and chats, etc., I'll be reading and following up on these and maybe adding them to my next Toolbox Tech Talks next Sunday at 2:00. Anyway, so I think it's time for the outro, the usual thing, just like and subscribe, press those little buttons and make my life better. And I'll see you all again next Sunday, 2:00. See ya. Let's do a little video. In stream.